This is stochastic processes, module 8, renewal processes. In the lecture 1, we have discussed a renewal function and a renewal equation. In the lecture 2, we have discussed the generalized renewal processes and renewal limit theorems. Markov renewal and regenerative processes are discussed in lecture 3. Non-Markovian queues such as MG1, MG1N, MGCC are discussed in lecture 4. GM1, GMC, GG1 non-Markovian queues are discussed in lecture 5. In this lecture, we are going to discuss applications of Markov regenerative processes. In the first half, we are going to discuss the steady state analysis of GAM1N queue. In the second half, we are going to discuss the application of Markov regenerative process in performance analysis of wireless networks. Already we have discussed the Markov regenerative theory in the lecture 3. It involves the Markov renewal sequence and embedded Markov chain. To study the limiting behavior, first we need the global kernel K of t, which consists of matrix elements Kij of t, and the another matrix local kernel, that is the matrix E of t, that consists of elements Eij of t, where I is belonging to omega dash, j belonging to omega. And also you need a mean time alpha ij, and also the steady state probability vector V, which can be obtained by solving V is equal to Vp and the summation of Vi is equal to 1, where I is belonging to omega dash. So we have explained the limiting how to find the limiting distribution in the lecture 3. In this lecture, we are going to discuss also the transient analysis, how one can find out the transient measures of the MRGP. Define V of t is the elements Vij as the conditional state probabilities of the MRGP. That is nothing but the probability that Z of t is equal to j given Z of 0 is equal to y0, that is equal to I, where I comma j belonging to omega. The sequence of yn is the embedded Markov chain of the MRGP Z of t. Also, one can write V of t is same as E of t plus K of t convolution with V of t. So, once you solve this equation, you can get the conditional state probabilities. The solution method is outlined as follows. First, you calculate the matrix global kernel K of t and the matrix local kernel E of t. Then find out the Laplace-Steele transform of K of t as well as E of t. That is the second stage. Then the third stage, solve the linear system for V of s, where V of s is the Laplace-Steele transform of V of t. In the fourth stage, invert V of s to obtain V of t. Once you know the V of t, that is a conditional state probability, you can find out the unconditional state probabilities using P of t is equal to P of 0 times V of t. That will give the time dependent state probabilities of MRGP. In the lecture 3, we have discussed only the steady state probabilities of MRGP. In this lecture, we are discussing the time dependent measures of the MRGP. Now we are moving into the steady state analysis of a GAM1N queue. Let Qt be the number of customers in the system at time t. Note that the evaluation of the system just after the departure of a customer depends not only on the number of customers Q of t, but also the remaining inter-arrival time of the next customer who is entering into the system. So, the evaluation of the system after the arrival of the customer into the system, provided the system is not fully depend only on the state of the system. Hence, Q of t is not a semi-Markov process. Suppose the time origin is taken to be the instant of before arrival, which is exactly j customers, then every time before arrival occurs, the system having a j customers, the future of Q of t after such time has exactly the same probability law as the process Q of t had starting at time 0. Hence, we can conclude the Q of t greater than or equal to 0 is a Markov regenerative process, MRGP. Here, the arrival instants are the only regeneration time epochs. That means that at the arrival epochs, the memoryless property is satisfied. Hence, the stochastic process Q of t is not a semi-Markov process, but it is a MRGP. Now we are going to study the steady state analysis. Now we are going to study the steady state behavior. Let nth customer arrive at the time point Tn. Let xn be the number of customers in the system before the arrival time instant of the nth customer. That is nothing but xn is equal to q of Tn minus 0. Number of customers in the system before the arrival time instant of nth customer. Therefore, since it is a Gi m1nq, the inter-arrival follows a general distribution and the service follows exponential distribution. Only one server in the system. The xn comma tn for n is equal to 0, 1, 2 and so on form a Markov renewal process or Markov renewal sequence. Suppose we define y of t is equal to xn, where t lies between tn to open interval tn plus 1, then yt will be a semi-Markov process having the embedded discrete time Markov chain, that is xn. Following the theory of MRGP, now we determined the global kernel k of t and the local kernel e of t. So, the kij of t is nothing but probability that x of 1 is equal to j with the t1 is less than or equal to t given x0 is equal to I for I and j belonging to omega dash. Whereas e of I comma j of t is nothing but the probability that x1 is equal to j with t1 is greater than or equal to t given x0 is equal to I. Here I is belonging to omega dash and j is belonging to omega. So, the omega is a collection of a set of states at all time points, whereas the omega dash is the set of states only at the regeneration time points, time instants. So, for this non-Markovian Qs, we will have a k of t matrix in this form with the kij of t is nothing but the integration from 0 to t of Pij minus 1 of x integration with respect to g of x, where g of x is the CDF of a inter-arrival time. For I and j is equal to n, we will have a different expression. That means the system would have come from n minus 1th state to nth state, or the system would have been stay in the same nth state, retaining in the nth state. Therefore, you have two terms in the integrand, p of n comma n minus 1 and p of n comma n. And the integration between the interval 0 to t, integration with respect to g of x. So here the pi of j are the transition probability, it's a one-step transition probabilities of the subordinated CTMC. Sorry, this is not the one-step transition probabilities. The pi comma j are the transition probabilities of the subordinated CTMC. The state transition diagram of the subordinated CTMC is shown below. So suppose the system starts from the state n, the p of n comma j of t is nothing but what is the probability that the system will be in the state j at time t, given that it was in the state n at time 0. So in the previous slide, the pi comma j are the transition probabilities of the subordinated CTMC. So you need for all values of I and j, and you have to find out the transition probability from this subordinated CTMC. So since the subordinated CTMC of this form, you can have the closed form solution for p I comma j of t for different values of I and j. Whereas the local kernel matrix is shown like this, and each entity's Eij of t is nothing but what is the probability that the system goes from I to j in the duration of 1 minus g of t. So once you know the matrix k of t and E of t, you can find out the steady state probability vector, as well as you can find out the mean time alpha I comma j. Once you know the steady state probability vector v bar as well as alpha I j, you can use the you can find out the steady state probability using this formula, that is pi j is equal to summation k is equal to 1 to n pk alpha k comma j divided by summation k equal to 1 to n bk of beta k, where beta k is nothing but summation over all L of alpha k comma n, where L is running from 0 to capital N. So to get the steady state probabilities of MRGP, first we have to find out the k of t and the E of t. Using these two, we have to find out the steady state probability vector v as well as alpha ij. Once you know the alpha ij as well as v, using the formula you can get the steady state probability for the MRGP. For the state probabilities, here the j is running from 0 to capital N. Now we are going to discuss the application of a Markov regenerative process in performance analysis of wireless networks. Here we are considering the handoffs in the wireless cellular networks. What is the meaning of handoffs? Whenever a mobile station moves across a cell boundary, the channel in the old base station is released and the ideal channel is secured in the new base station, and this process is called the handoff process. and the corresponding calls are called the handoff calls. Handoff is an important function of mobility management in wireless cellular networks. Handoff arrivals are known to deviate from the Poisson assumption. Usually, the handoff arrivals are assumed to be Poisson process, but usually the call arrivals are following a Poisson process, but the handoff arrivals are deviate from the Poisson assumption. When handoff inter-arrival time follows a general distribution, usually all the calls inter-arrival time follows a exponential distribution. Therefore, the call arrivals follows a Poisson process. When the handoff inter-arrival time follows a general distribution, then the question is how to obtain the performance measure. Closed form formulas for the performance measures using Markov regenerative process theory can be applied. So one can use a Markov regenerative process to find out the closed form formulas for the performance measures. Whenever the handoff inter-arrival time follows general distribution instead of exponential distribution. So here we make the assumptions for the cellular system. The cellular system is homogeneous and cells are identical, and assume that it has a capital C channels. Out of that, G channels are God channels, and these God channels are reserved for handoff calls. Also, we assume that the new calls are follow Poisson process, whereas a handoff calls arrival follows a non-Poisson. Also, you assume that call completion, whether within the cell or handoff to the neighboring cells, follows a exponential distribution. The important assumption is that inter-arrival of handoff calls follow general distribution with a finite mean. Therefore, we are using Markov regenerative process to find out the performance measures. If the handoff calls inter-arrival also follows a exponential distribution, with the proper setup, one can study the performance analysis of one can find out the performance measures using a continuous time Markov chain. And since the inter-arrival of handoff calls follow a general distribution with the finite mean, we are going to use a Markov regenerative process. So the new call arrival follows Poisson process, whereas the inter-arrival of handoff calls follows a general distribution, and totally we have capital C channels. Out of that, G channels are God channels, which is reserved for handoff calls. And call completion as well as the handoff to the neighbor calls are exponential distribution. If you see the state transition diagram of this process, that is Z of t, is nothing but the number of talking channels, talking calls at any time in the system. The question is whether Z of t is a continuous time Markov chain, or Z of t is a semi-Markov process, or it is a Markov regenerative process. The underlying stochastic process Z of t denotes the number of ongoing calls or number of talking channels in the system at time t. It is not a continuous time Markov chain because the sojourn times are not exponential distributed. It is also not a semi-Markov process because whenever the channels are busy and the call completes, we have to keep track of the remaining handoff inter-arrival time in order to predict the future behavior. Therefore, this is not a semi-Markov process, as well as this is not a continuous time Markov chain also. Whereas Z of t is a semi-Markov, Z of t is a Markov regenerative process. So, we are going to study the performance measures using Markov regenerative process. We have two performance measures. One is called a call blocking probability, the other one is called the call dropping probability. The call blocking probability is related to the new calls blocked, whereas the dropping probability is related to the handoff calls dropped. So, the new call blocking probability is nothing but the percentage of new calls are rejected. Handoff calls dropping probability is nothing but the percentage of calls forcefully terminated while crossing cells in the cellular system. Using the same theory of a Markov regenerative process, first you create the global kernel, then create the local kernel, then obtain the steady state probability vector V case, also find out the mean time alpha I comma j. Using that we can find out the steady state probabilities. Here the lambda h is the rate of inter arrival time of new calls, of handoff calls. Once you know the steady state probabilities, you can find out the blocking probability as well as the dropping probability. The blocking probability is nothing but the summation of the system state from C minus G to capital C. Whereas the dropping probability corresponding to the handoff calls, that is nothing but the probability that all C channels are occupied and given that the handoff calls has arrived. That is nothing but the steady state probability of B suffix C. So, the solution method is compute k of infinity from the k of t by making limit t tends to infinity, and solve the linear system V is equal to Vp, where P is k of infinity. Then first we find out the steady state probabilities, then obtain the performance measures of a blocking probability as well as the dropping probabilities. So, here the global kernel k of t will be of this form. Similarly, the local kernel E of t will be of this form with the rows, C rows and C plus 1 columns, because here the omega dash is 1, 2, 3 and so on till capital C, where omega is 0, 1, 2 and so on till C. Using the proper numerical values for the inter-arrival time, you can find out the blocking probabilities versus the number of channels. If you increase the number of channels capital C, then you can find out the blocking probabilities for various values of C, and as number of channels C increases, the blocking probability decreases. And we can verify with different distribution. You can choose a 3-stage Erlang distribution or a hyper exponential distribution, as well as we can choose the exponential distribution. Then the underlying model will be a continuous time Markov chain, and you can compare the blocking probability results for the various distributions for inter-arrival times of handoff calls. by fixing fixed mean and of inter-arrival time. Similarly, you can numerically illustrate the dropping probabilities versus number of channels or the different distributions for and of inter-arrival times with the fixed mean and of inter-arrival time. We can illustrate the blocking probabilities versus the one divided by mean and of inter-arrival time also. That means that this is the rate. So as the rate increases, the blocking probabilities increases. The rate of hand of inter-arrival increases, the blocking probability increases for the various distributions. Similarly, as the rate increases, because the x-axis is 1 divided by the mean hand of inter-arrival time, therefore 1 divided by mean time is nothing but the rate. So as the rate increases, the dropping probability increases for the various distributions also. In this lecture, we have covered as application of Markov regenerative process with the GM1NQ as well as the application of Markov regenerative process in performance analysis of wireless networks. Here are the important reference for today's lecture. So consider a cell which has a C channels. Let Z of t is nothing but number of ongoing calls in the system. Here the system is nothing but SL at time t. We have made the assumption the new calls arrival follows a Poisson process with the parameter lambda n, whereas a handoff calls arrival follows a non-exponential, inter-arrival follows a non-exponential distribution or general distribution with the finite mean 1 divided by lambda h. Omega is the collection of possible states whereas omega dash will form a regeneration time points, the states corresponding to the regeneration time points, that is going to be 1 to C. Our interest is to study the limiting behavior of the So the state transition diagram for this model is going to be and so on. C minus 1. So these are all the possible states. Suppose the new call arrives, then the system size is 1. Suppose one more new call comes, the system size goes to 2 and so on. So like that, the system size can be incremented by 1 by 1. Similarly, when there are C minus G minus 1 channels are already ongoing, then if one more new call comes, then the system goes to the size C minus G. But since handoff calls are having the higher priority, already small g channels are reserved for handoff calls. Whenever remaining G channels are available in the system, then those channels are reserved for the handoff calls. Therefore, no more handoff arrivals whenever the system size is goes from C minus G onwards till C. Similarly, if the system size is 0, there is a possibility of handoff call arrival. So that I make it as a dotted line with the distribution capital G. Whenever the system size is 1, there is a possibility of handoff arrival, therefore the G comes here. Similarly, the handoff arrival can occur to lead the system sizes C minus G minus 1 also. And similarly, whenever the system size is C minus G minus 1, there is a possibility of handoff arrival, therefore G. But whenever the system size is C minus G, that means at this time C minus G calls are ongoing, that includes the handoff call as well as the new calls. If new calls arrives at this time, it will be blocked. Whereas if handoff calls enter into the system, it will be entertained. Therefore, you have an arrow, dotted arrow throughout from 0 to C, because handoff calls are allowed as long as at least one channel is available in the system. Whereas the new calls are allowed to enter into the system whenever more than G channels are available in the system. Therefore, the lambda n is exist from 0 to 1 and 1 to 2 and so on till C minus G. After that, there is no arc with the lambda n. Now we discuss the departure part. Whenever the call can be completed within the cell, or the call can be hand off to the neighboring cell. Suppose we make the assumption mu1 is the rate corresponding to the call completion time, and mu2 is the rate for exponential distribution for the handoff to the neighbor cell, handoff out to neighboring cells, with the assumption that both are independent, then you can denote mu as mu1 plus mu2. Now, suppose the system is in the state 1, either one new arrival can occur or one handoff arrival can occur, or this call can be completed within the cell, or this call can be hand off to the neighbor cells. Since both are independent, each one is exponential distribution with the parameter mu1 and mu2 respectively. Therefore, the system size goes from 1 to 0 is mu. The system goes from the state 1 to 0 will be with the rate mu, because mu is mu1 plus mu2 and mu1 is nothing but the rate of call completion, and each time is exponential distribution. Similarly, the handout to neighboring cell, that is follows exponential distribution with the rate mu2, where mu is equal to mu1 plus mu2. Similarly, the system comes from the state 2 to 1 will be 2 min, because there are two calls are ongoing. Any one of the ongoing calls can be completed or hand off to the neighbor cell. Therefore, the system goes from the state 2 to 1. Therefore, the rate will be 2 times min. Similarly, the system goes from C minus G minus 1 to C minus G minus 2 will be C minus G minus 1 times min. Similarly, you can fill up this rate will be C minus G times min. This will be C minus G plus 1 times min, and so on. The last one will be C times mu, and the system moves from the state C minus 1 to C, that will be, that is with the dotted arc, that is G with the dotted arc. Whenever the system size in the state C, there is a possibility of still the handoff arrival can come, but it will be dropped. Therefore, there is a self loop with a dotted arc. Again, the system size will be C. So, this is a state transition diagram of the Z of t stochastic process. Z of t is nothing but a number of ongoing calls in the system at time t, and the possible states are 0, 1, 2 and so on till C, and the dotted arcs are related to the handoff arrivals, whereas the other two arcs are corresponding to the new call arrival and the call completion. So, the handoff calls are possible and enter into the system whenever the system size is from 0 to C minus G minus 1. Whenever the system size is from C minus C to C minus G to C, the new calls are blocked, and whenever the system size is C, the handoff calls are dropped. Now, the Z of t, this stochastic process is a discrete state continuous time stochastic process. Now, we are going to analyze whether the Z of t is a continuous time Markov chain, or it is a semi-Markov process, or it is a Markov regenerative process. First, the new call inter-arrival times are exponential distribution, which is independent of handoff inter-arrival time, and also it is independent of call completion. The call completion times are exponential distribution, all are independent also, whereas the handoff call inter-arrival times are a general distribution with a finite mean. Therefore, the sojourn times in each state of this stochastic process Z of t is not a exponential distribution, because of handoff inter-arrival times are general distribution. It is a non-exponential distribution. Therefore, Z of t of t greater than or equal to 0 is not a continuous time Markov chain, because of sojourn times are not exponential distribution. Since the Markov regenerative Markov property is not satisfied at every time instant, the system is entering into all the states, the Z of t is not a semi-Markov process. Here the Markov regenerative property is satisfied whenever the time instant at which the arrival of a handoff calls occurs, not for the time instant of a new call arrival occurs or the call completion occurs. The time instant in which the system moves to the different states because of new call arrival or call completion, inside it is a call completion within the cell or handoff to neighbor cells. But only the time instant at which the handoff arrival occurs, those time points the Markov property or the memoryless property is satisfied in this stochastic process. Therefore, the Z of t is not a semi-Markov process. But if you see the Markov regenerative process theory, the probabilistic replica exists whenever the handoff arrival occurs. Therefore, the state 0 is not corresponding to the regenerative state, whereas the states 1, 2 and so on till capital C are the regeneration states corresponding to the regeneration time points with respect to the handoff arrivals. So, the conclusion is Z of t is a Markov regenerative process which is not a continuous time Markov chain and which is also not a semi-Markov process. If we assume that the handoff inter-arrival times are exponential distribution which is independent of new call arrival as well as independent of call completion, then the Z of t will be a continuous time Markov chain. So, our interest is to study the new call blocking probability, because in these states the new calls are blocked. Whenever the system is in the state C minus G, C minus G plus 1 and so on till C, the new calls are blocked. Whereas the handoff calls, you can see the dotted arc till C. Therefore, the handoff calls are dropped whenever the system is in the state C. Therefore, our interest here are the new call blocking probability as well as the handoff call dropping probabilities. So, whenever a new call is attempted in a cell covered by a base station, the new calls is connected if an ideal channel is available in the cell. Otherwise, the call is blocked. The new call is blocked if an ideal channel is not available in the channel. Because of a God channel policy, whenever more than or equal to more than G channels are available as a ideal channels, then the new calls are accepted. Whereas the handoff calls continuously if an ideal channel exists in a target cell, the handoff call continues nearly transparently to the user. Otherwise, the handoff calls is dropped. So, here whenever the system state is in the state C, the handoff calls are dropped. So, our interest is to find out the loss probabilities such as new call blocking probability and handoff call dropping probability. The new call blocking probability is denoted by the letter P suffix P, and it's a function of a C comma G. That means the total number of channels as well as the total number of God channels. By fixing the total number of channels as well as the total number of God channels, one can find the new call blocking probability for a cell. That is nothing but the percentage of new calls are rejected. So here it is nothing but what is the probability that in a long run the system is in the state 0 to in the state C minus G to C, that is the so the percentage of new calls are rejected will be the new call blocking probability. Similarly, the handoff call dropping probability in a cell, that is denoted by P suffix D, and it's a function of C with G. That is nothing but the percentage of calls forcefully terminated while crossing cells. So here we are finding the two loss probabilities. One is new call blocking probability and the other one is a handoff call dropping probability, and both are steady state probability measures.
In this course, we have discussed the performance analysis of wireless networks as an application of stochastic processes by keeping various stochastic modeling techniques in the mind. However, this is a brief insight into the application of the techniques to the real world problems.
Thanks.